So now we're at the last spot where we picked up for chapter 15. We were talking about drawing without replacement, which means you take a thing and then you do not return it back. And so I want you to think about this in terms of our visualizations before, and we've been looking at a lot of these bifurcation or two choice things, these binomials, if you will. Uh, and when you have a bifurcation or a binomial, a tree diagram is often helpful. So a tree diagram helps us think through conditional probabilities by showing sequences of events as paths that look like the branches of a tree. A tree diagram can help you find the probabilities, or the counts, for both independent and dependent events. So unlike a Venn diagram or even a contingency table, this really shows us when it changes those conditional probabilities we can calculate. And notice that at the very end, if you just added up these values, those obviously add up more than 1. But what's happening is you're doing a half times a half, or a half times a half. And those combined probabilities of 2 boys, or a boy and a girl, or a girl then a boy, and then 2 girls, if you add all of those end probabilities up, those combinations, that will be your total of 1. So suppose a family has 2 children born apart. It's safe to assume that it would be equally likely. But now, if you want to get real about this, and I highly suggest you click on this link, and it will take you to this fascinating article of what are the odds of having another boy or a girl. And it turns out that anecdotal information that you're given, now, spoiler alert, did you know that if you hit this 3 letters at the top of the screen, you will get this into reader view? Ooh. So if we sampled over 6,000 American families, we come to find out that boys are born 51% of the time and girls are born 49% of the time. And you might be finding that interesting. And it turns out this is more biological. You can ask one of our biology teachers about this, but males are more fragile. Male infants are less likely to survive their first year, and a man's expected lifespan is less than a woman's. The slightly higher conception rate of males is nature's way of evening out this imbalance. And Dr. Shettles theorized why bearing male producing sperm may have a speed advantage over X bearing female producing sperm, more often winning the race to fertilize the egg and resulting in more male conceptions. And nature is fascinating. I highly encourage you to read that article. So let's say we look at this and say the chances the initial boy was 51%, and the probability of the initial girl is 49%. Well then, if you know that you had a boy, the probability that the next child is a boy is 50%, and the probability the next child is a girl is 50%. Interesting. Well then, what happens is we get our probability of 25%, 25-50, 25-50 for having 2 boys or a boy and a girl. But this conditional probability, which is based off of the article, is if you have a girl, then the chances are girl, what's the chances you have a boy given girl? It's actually 54.5%. When drawing a T diagram, completely fill out the diagram. I need to see all of these values filled in appropriately. Now, your book has an example of a tree diagram showing the probabilities of drinking and driving accidents. I don't know what it is, but this textbook loves making examples of drugs and alcohol. So the events of drinking and an accident are dependent, which makes sense. All the final outcomes are disjoint and must add up to 1. So we can find the final probabilities to find the probabilities of compound events. So we have people surveyed, 44% chance that they're a binge drinker, 37% they're a moderate drinker, and 19% chance that they abstain. And then we have the chances that each of them get into an accident. So 17% chance that binge drinker gets into an accident, and 83% chance that they have no accident. So to find the compound probability would be 0.44 times 0.17 gives us 0.075, or 7.5% chance. 0.44 times 0.83 gives us 0.365 or 36.5% chance. You can see as we work down each of these to get the final result is the product of each. So there's a little bit of multiplication involved. Once we have these, then it's far easier to find these conditional probabilities that we're looking for. For example, let's talk about replacement. Easiest example that math teachers go to is marbles in a bag. So suppose we have a sack of 12 marbles, 4 blue, 3 white, and 5 red. A marble is selected, and the color is noted. It's not returned. So when it says not returned, this is no replacement, which means we will have one less marble in the bag each time. And a second is selected. The appropriate tree would be as follows. Well, we know we have 4 blue, 3 white, and 5 red initially. So we indicate that. These are all the marbles. So we have a 4 in 12 chance of being blue. Well, now we know that there are less blues in there, and there's less total marbles in there. So there's 11 marbles left. There's only 3 blues in there, 3 white, and 5 red, because those didn't change. Or 3, then 2, or 5, then 4, and everything drops down. So now, you can see this gets quite messy quite quickly. We have the probability that both of those events occur, blue and blue, blue and white, blue and red, etc. And we multiply those events. If we summed up each of these end probabilities, we would get our total of 1. Now what about reversing the conditioning? So reversing the conditioning of two events is rarely intuitive, but it is simple algebra. Suppose we want to know the probability that A happens given B already happened. And we know probability of A, we know probability of B, and we know B given A. We also know A and B because that arrives from our formula here. Note, probability of B given A is A and B divided by the probability of A, which is another way of rewriting this formula right here. So from this information, we can find the probability of A given B. So we started here. We know this. What we want is to have the probability of B given A. So what we're using is this original part to find the and, to then find the reverse directionality. So let's go back to our birds example. If I want to know the probability of first I'm given probability of B given A and the probability of A given B. Notice, again, the A and the A match. Second denominator. The B and the B match. Second denominator. I want to know what's the probability that we have a reptile given that it's foreign. So I want to look at reptiles that are foreign. So I have my 64 divided by the total number of reptiles. Probability that reptiles given foreign, and if that's foreign, then that is 64 over the total of foreign, which is 498. Excuse me for my notation mistake. Last thing. Everyone's familiar with a deck of cards, correct? So a card is drawn from a deck of cards that has 52 in it. What's the probability it's an ace or red? Well, there's 4 aces, there's 26 red cards, and there are 2 red aces. So in order to find that probability, we take 4 plus 26, which is 30, subtract 2, which we get 28 out of 52, or 7 out of 13. Interesting. The 2 cards are drawn from a deck of cards without replacement. That means they can't be independent. What is the probability that both are aces? So realistically, the draws are not independent, which means they're conditioned on each other. So we first have to say the probability of getting an ace and an ace is the probability of getting an ace the first time times the probability you get an ace the second time, given you already have an ace the first time. What this turns out to be is as simple as you think. We have 4 aces and 52 deck of cards. Times, well, now there's 3 aces left. We're assuming you got the first one right. Only there's 51 cards left in the deck of cards. Notice that these reduce as we have more conditions on them, which is what we would think it would be. But most of the games of chance that people play with cards are a little more complicated. Take, for example, a poker hand, 5 cards that you're given from a deck of cards. What's the probability that all cards are a heart? Again, the draws are not independent. If you get a heart the first time, then the probability you get a heart the second time is contingent on the first one. Or if you have 2 hearts, what's the probability you get a third heart? So each time we take this into account, we have to reduce the number. And so what we do is we say 13 out of 52 for the first heart. Well, let's say we were successful. There's 12 left. And then there's 51 cards left over. So we reduce it down to get a second heart. And then a third heart, we reduce each of those down again. And then a fourth heart, we reduce it down again. And then a fifth heart, we reduce it down again. And then we take each of those fractions, multiply it all out, and get 0.0005, or 5/100th% chance of this happening. Now, if I draw one card and look at it, and I tell you it's red, what's the probability it's a heart? That phrasing is conditional, so it should limit the sample space. Once I tell you I draw a card and tell you that it's red, there's only 26 cards in the deck. Now, if we're looking at this, and we know that they're not independent of each other, we can say, what's the probability of getting a heart given red is just the probability of heart and red, which is 13 out of 52, because all hearts are red, times the probability of having a red, divided by the probability of a red card, 26 out of 52. The 52s go away, which gives me 13 out of 26, which is what we expect if we're saying we're limiting the space that we're looking at. It's easy to make these formulas more complex than they have to. Just think conditional is limiting where we're looking. So let us suppose we notice who is wearing jeans in class one day. Obviously, that's not going to be very frequent. The table at the right shows the counts. We have males and females in our class, and we have jeans and others. Skirts, pants, khakis, whatever. So using this contingency table, what's the probability that a male wears jeans? Notice, what's the probability that a male wears jeans? It's the probability that the person's wearing jeans given that they are male. So what I want you to look at is what's the intersection between male and jeans divided by the probability that they are male, which is 17. And that's what we should get, 12 out of 17. What's the probability someone wearing jeans is male? Again, this is the reciprocal of this. This is the flip. So what's the probability that they are male given they're wearing jeans? So let's switch to a slightly different color. Again, our intersection is 12, but in this time we're saying we are given that they're wearing jeans. So it'd be 12 out of 20. Now the question goes, are being male and wearing jeans disjoint? Disjoint means they share nothing in common. Obviously, we see that there is overlap between males and wearing jeans. It's not 0, so they're not disjoint. Okay, I promise that we're going to keep this short. So there's a couple more chances, or a couple more problems. We'll just fly through these. There's a 30% chance of rain tomorrow. When it's raining, Papa Oscar takes the bus to work 50% of the time, and Mommy drives him 50% of the time. When it's not raining, Papa Oscar takes the bus 25% of the time, and Mommy brings him home 75% of the time. Mommy ain't going out in the rain. Got it? So what's the probability that Papa Oscar, let's call it PO, takes the bus tomorrow. Notice, I gave you a piece of information to start. There's a 30% chance of raining. So we first have to look in this tree diagram. Well, 30% chance it rains, 70% chance it doesn't. Then we were given information, it's a 50-50 shot when it's raining, that either the bus takes him or mom takes him. So we have 0.3 times 0.5 and 0.3 times 0.5. So we have 50% chance of either of those occurring when it rains. Additionally, when it's not raining, it's a 25% chance that he takes the bus and a 75% chance that mom takes him to school. So again, we multiply down the tree to get those resultant probabilities. So the probability that Papa Oscar takes the bus is when does he take the bus in either of these cases. So it's either rain and bus or no rain and bus, which would be 0.15 plus 0.175, or given 0.325. And that's how we utilize this visual to find out where these resultant probabilities come from. Now, I personally think this problem is super important. I think ovarian cancer is a very serious disease. I'm going to save this for in class at the end of this week. The last thing I want to point this out again. If you see at least, often it is easier to find the probability of an event not happening, which is the converse, or the complement, I should say, than it is in finding the probability the event will happen. Then we can subtract from 1 to find the probability of the event. That's how we find complements. I'm not certain how often I must repeat this until it finally sinks in. But when you see the words at least, you should consider the complement. At least 1 is the same thing as not 0. Let me repeat that. At least 1 is the equivalent of not 0. You'd be surprised at how many people miss something like that. This is a little too close to home with everything that's going on of averting nuclear war. So let's just review. We've learned that A or B is the probability of A plus the probability of B minus the overlap. When two events are disjoint, we say mutually exclusive, then the probability of A and B is 0, aka we have no overlap. If two things are independent, the probability of A and B happening is just the multiplication of the two. When two events are independent, then the probability of B given A is equal to the probability of B. Now, where does this formula come from? This probability of B given A is A and B all over probability of A. So notice, if this is equal to the probability of B occurring, then when we cross multiply, we get the probability of A and B equals A times B. The only way I can really prescribe you to get better at probability is just doing the problems. The more you do these, the more you're able to maneuver through these situations. This work is not easy. Not easy by far. So take your time, work through the problems, and ask questions. I'll see you in the addendum to this next time, Falcons.